how would you debug issues which might have been caused by memory corruption, right? One rule of thumb, whenever you have to use memory, especially flash, I have come across a lot of issues where writing to the flash and for whatever reason, the firmware got reset or the power was removed, and then when you come back and it's corrupt, flash is corrupted. There are a few things. One of them is to whatever you write or read from whatever you write to the memory, attach a CRC to it. A lot of controllers, a lot of microprocessors have hardware CRC, which go through, like, they calculate CRC pretty fast. If not, like even doing that on, like, depending how big is like on a 256 um, byte memory size or memory like struct or whatever you're trying to store, it's not that huge. So what it allows you to do is, like, if memory corruption happens, you can at least detect it, that a memory is corrupted, as opposed to getting into a situation where you read that memory and your software doesn't, like, code firmware embedded system software is not taking into regard that it could be corrupted. So usually that helps a lot. So that's the best way to preemptively check if the memory is corrupted or not. That's one way. The other way is basically, like, there are ways, even if you don't use CRC, where you can check if the memory is correct, but CRC is the best one. Yeah, there are some hacky ways, but I have seen at the end of the day, CRC is the best way to check. Now, how would you debug issues which might have been caused by memory corruption? So if your memory is corrupted, another way that I would tell you is, so that you can prevent such an issue from happening, is that, especially if you're working on a system where it's possible that the power is removed or the battery might die or something like that, like it's a battery power, then it's kind of, and you have to write something to the memory. One thing that you can do is that, okay, so the first one I said was basically add a CLC. The second is basically you have a staging area. Before you write to the memory, you basically have a staging area. You write to that first. So the way it would work is that, let's say that you have some piece that you have, let me draw some memory. So you have this memory. This is, let's call this backup. Now everything that you want to write to the backup, everything you want to store needs to be stored into the backup. So let's suppose there's some information that you want to store over here. Let's call this XYZ that you want to store. Now let's say that you wrote X. Even if you had CLC at the end of this, like XYZ, and then there's a CLC attached to it. Let's suppose you wrote X to it, and then suddenly the power was removed. Now you are in a state where you have written X, but and you have overwritten the previous backup, but now you cannot use the newer one, because the over here the CLC would tell you that, okay, this CLC, like, let's say this older CLC was CLC1, the newer CLC is going to be CLC2. So you wanted to write XYZ CLC2, you wrote X, and then the power was removed, or it was yanked, or you crashed, or whatever happened. Now you're in this weird state where you don't have the previous data and you don't have the new data because a reset happened. So what they usually do is that there's the technique where, for the same scenario, let me rub this. So for the same scenario, what they do is that they set up a staging area. So there's a backup and then there's a staging. So now you wanted to write XYZ and CRC2. And let's say that there was CRC1 over here, and there was ABC written in the ABC. Not really used to the Apple Pencil yet. So there's ABC over here. So you write XYZ to the staging area, and if you are successful in writing XYZ to the staging area, only then you write it to the backup. If you Because in this way what happens is that if for whatever reason you wanted you when you were trying to write to the staging area, let's say that in this scenario you wrote only X and Y and you were not able to write Z and C, what would happen in this scenario is that sorry, you were not able to write Z and CRC1. What would happen in this scenario is that you then boot up, then at least you have a backup, something, some old data that you can rely on, and basically at least continue from there. So it's kind of like something to fall back on. And if you were able to write to the XYZ to the staging area and also were able to write the CRC2 over here, and now you were trying to basically, you wrote it over here, and now you were trying to go from staging area to backup, and you were only able to write, let me up this, you were only able to write X and Y. So now you have a recovery mechanism over here. What it allows you to do is that you were able to write X and Y, and but you were not able to write Z and CRC2. Now, when you boot up, you check, oh, if my is my backup correct? If your backup is not correct, you can then go to the staging area and you can get whatever was written over there. So this way, you're because you are doing it in two steps, it ensures that one of them has valid data in there, and the CRC should match. CRC should be able to tell you that one of them has valid data. Now the question is that if both of them have valid data, valid CRC, how would you know that which one is correct, right? So usually to be able to see if which one is correct, usually what they do is like they add another field to your data, and this could be sequence number or something. Basically, the idea is that you increment the sequence number each time you are trying to override the previous data. So using that, you can tell which one is newer one, which one is older one. These are some of the like I've just talked about some of the basic ideas around it. How you can basically avoid getting into a situation where the memory is corrupted.
So in a file system scenarios, we have something called journal. So staging looks very similar to journal, right? Is that
Yeah.
a correct answer?
Yeah. I mean, if you're looking at a higher level operating system, yeah, they're provided by like they provide all of this built in, right? And they also some of them even have like recovery, like they stage it and basically they have like two copies so that they are not trying to overwrite the like in this scenario the backup. There's a good example of another one which is Little FS, which is designed to work on systems where you have where you the power can be removed. So it's like power failure safe. So like even if a power fails, it is safe from that. Um, and then if you further go into it, there are some systems which even provide like a full backup. Like they basically have two copies. But of course, they're like going into um, like now the implementation is much more complicated for them, and you also need bigger memory space, which are some of the systems is very or applications are is constrained. So depending on how much, like if you can run like for Linux or embedded Linux, then the number of tools and the number of features that are available to you are much more bigger.
Okay. Um, and this is the memory corruption in the context of flash memory or persistent storage. What if there is a corruption, let's say in the RAM, like DRAM, when the software is running, and that manifest as some weird bugs, sometimes like either a buffer overflow had overwritten some adjacent data structure, or some random, like if we have, let's say, done a DMA, and then DMA has wrote, either a DMA hardware has a bug and it wrote to the address which it was not supposed to write. And in those scenarios it becomes even more harder, right? Because
Yeah, yeah. And those scenarios, like sometimes it's, yeah, those scenarios, it becomes really, really hard. And a lot of times it becomes so difficult. Like sometimes you wouldn't see any issue, but in next commit, you would start seeing issue. And like I have been in such a situation where we the number of GPIOs increased, but the array for it was predefined. It was part of a static library. So the number of arrays, like actual space for it, was statically defined in the library, which was not updated with each new app. But the actual number, the macro which corresponded to that, kept incrementing. And it was interesting that sometimes it would crash upon boot up when we were trying to initialize all those GPIOs, and sometimes it did not. It just depending on where in your data or the BSS your array is. If there's some value after that which corresponded to null, or it corresponded to something which didn't caused us a memory segmentation, it was faulting or not faulting. So there's for such a scenario, that's a good one. So I do have some more questions. One of them deals with the stack overflow, um, which might answer some of the concerns uh, with the RAM memory corruption, or RAM misusage of RAM in memory. That would answer some of your question. If any, there's still any other, let me know once I've gone through that.
I have a quick question here.
Yep,
So in this staging part, I believe the backup and the staging copy just resides in the same memory, correct?
yep.
And in case when you're doing a copy to the staging part, and when the battery is being removed, does it mean that next time what it does is it's going to roll out, do a recovery mechanism here, rolling out the backup because you have not successfully write the full data? How would that happen?
Yeah, so this staging or backup is let me give you a little bit context. It's really useful for scenarios like when you want to do like ADC, like an update of something like ADC calibration, right? There's an ADC calibration which is done in the factory, and then like every once in a while, if your firmware is set up that do the ADC calibration at different temperature or at customer location or at different state, right? So now you need to update it, but you don't want to lose the initial, which will either done at the factory or the last time the ADC calibration will done. So in that, now thinking with that example, as long as with like what I really care about is like I don't want to be in a state where I have no ADC calibration data, so that like as long as I don't have the latest one, I have the one before that, the n-1 iteration, I'm okay. Even if I lose the nth iteration. But with this approach, let's say that this one was the 1000th and this one was 1001, right, iteration of the data. Now the question is that how do we figure it out, like which one is which one? If we have the sequence number, if we do care that okay, which one we want to get to, so the first thing you would do when you would boot up or when you would reset or after a crash, you would look at both of the CRCs. If both of them are correct, then you look at the sequence number. Whichever one is the newer sequence one, you basically use that. But if one of them is corrupt and the other one is not corrupt, you use the one which is not corrupt. Does that answer? Like, does that give you an idea, like what would the code flow be like?
Yes. Thank you.
Yeah. Sure, no problem. So CLC is the other one basically is staging. Um, yeah, yeah. These are the two main ones. Then anything you kind of build on top of it, it starts becoming more complicated, and you at that point you're basically building on top of it. Like I said, like the third one is that backup. And when I say backup, that's different from it. It means that you have redundancy in the system. You have redundancy, which like I said, like if you can keep two copies of it, then that's one way. Another one that's actually used, it's used in very specific scenarios is that, let's say for whatever reason, like you have a memory card, right? And for whatever reason, the whole memory has become corrupted, and it's out of your control. What I have seen in one application, what they did was that they had a default data set that was default small data set that was stored as part of the flash, and that's what that was their fallback. If, like, assuming like someone stole the memory card, or memory card was not there, or if it completely became corrupted, and for whatever reason, like there was a hardware failure, at least there's like um, backup copy, or you can say like default values in the flash, and as part of your code, wherever your code resides, it's part of that. Because the idea is that if nothing else, you have a copy in the copy, or it could be even like a constant, like a set of constants within your code. And the idea is that if everything fails, that's fine, but if your code fails, then there's no way to recover from that. So as long as that doesn't happen, like when I say your code fails, like wherever your code is stored, if, like, for instance, like even your flash fails, then there's no point. At that point, like it's like a brick device. There's no way to recover from that. I wouldn't say brick. I would say that it's a device which has no app image on it. Maybe you can recover from it by, like, bootloader can maybe recover by installing a new application or something like that, or connecting to a phone, or connecting to cloud or something like that, like depending on how smart is your bootloader, and install a new firmware image or embedded software image. But yeah, so that would be the other one.